Kia ora and welcome to question 5 of the 2011 Skull Calc exam. This one's pretty much all complex numbers. Part A is a pretty left field scholarship question. Occasionally you get different functions that you might never have seen before unless you have a wide reading appetite for mathematics. Part B and Part C are fairly standard, but extension on what you would have learnt at level 3. Particularly Part C, where you really need to understand your geometry to make the problem more straightforward. Anyways, Part A introduces this thing called a gamma function. Have a look, read it up on Wikipedia, it's quite interesting. This gamma function extends the factorial function to all of the real numbers except for the negative integers and 0. It takes values of the factorial function at positive integers and has the property that for any values, the gamma, it's like a backwards t kind of thing. Sorry, not backwards t, just looks like a t without its other branch. It's like in stats and probability with the union formula. I always call this an upside down n and upside down u, even though it's just a u and an n. Never mind. So we've got this gamma function which apparently has this property. Okay. We also have the gamma function for integers or positive integers equals to this. Alrighty. What's the question asking us to do? Oh, there's another formula. A reflection formula. My goodness. So we've got heaps of formulas and we have to somehow work out how to use them to answer the problem. So this would be a question that would blow away some people because you need a bit of resilience to be throwing all this random stuff and make sense of it. In scholarship with 4 questions, as I'm videoing this, the scholarship exam's moving to 4 questions. You have 45 minutes per question, so we'd have 15 minutes for this subpart. So we really can take our time to think about it. Of course, that doesn't make for a very good YouTube video though. Okay, what do we need to find? The exact value of gamma 1/2, and hence the exact value of gamma 5/2. Okay, so it's telling us where to start. Now, the gamma value of 1/2, we could try, should we try the first formula? Does the first formula work for us? 1/2 minus 1 times the gamma value of 1/2 minus 1. No, that doesn't seem to be taking us the right way because it's going to take us into gamma values of negative numbers. And we're going away from something that we actually want. We want the gamma value of 5/2. So let's switch it around and go, okay, what about the gamma value of 5/2? That's going to be 5/2 minus 1 times the gamma value of 5/2 minus 1, right? So 5/2 minus 1 is 3/2 times the gamma value of 3/2. Okay, we're making progress. We've got closer to 1/2. And then if I find the gamma value of 3/2 using the same first formula, 3/2 minus 1 times the gamma value of 3/2 minus 1, that's 3/2 times 1/2 times the gamma value of 1/2. And there we go, that's what we need to find to be able to find the gamma value of 5/2. So we've exhausted all of our options for the first formula because, like I said, when we put 1/2 into it, it went into negatives, which means we can't use the other gamma function. But what we can do is use the third formula. So the reflection formula, gamma of 1/2, making z 1/2, multiplied by gamma of 1 minus 1/2. Oh, that's cool because 1 minus 1/2 is also 1/2, equals pi over sine pi/2. Sine pi/2 is 1, so we've got the gamma value of 1/2 squared equals pi. The gamma value of 1/2 therefore is square root pi, and assume it's positive there, therefore the gamma value of 5/2, my t's are now looking like r's, is equal to 3/4 times root pi. Okay, part B. Consider this power of 6 equation. Oh my goodness. Okay, it's not too bad because it's 6, 4, 2. It doesn't have any odd powers in it. But we're going to try and solve it, find the other 5 roots, given that we know one of them is root 2 plus root 3i. So just thinking to the stuff that you'd do at level 3 for complex numbers. NCA level 3, we solve problems like z to the 6 equals a complex number. We might solve quadratics, or we might solve cubics with coefficients. I'm just being lazy. So you might solve something like that, but you'd need to know what one of the solutions was first to turn the other bracket into a quadratic. They are the only two sort of types of problems you get at level 3 NCEA. So for scholarship, the problems are going to use that mathematics, but just in quirky ways. Okay, let's write this equation out. We've got x to the 6 plus 2 minus k, x to the 4 plus 25 minus 2k, x squared minus 25k equals 0. And we're told one of the roots is root 2 plus root 3i. C equals root 2 plus root 3i. Okay, first up, think about what the even power stuff is telling you. When you have a polynomial that is only even powered, if we sub an x to it, it's going to work if it's a solution. If we sub a negative, whatever the solution was, it will also work. So actually we know that C1 might be that. C2 is also going to be the negative of it, because even powered. So that's helpful. For example, if x squared equals 9, right, plus or minus 3 is the answer. Whatever the solution is for the positive, the negative will also be a solution. And that's the case for any even-powered polynomial. We also know that the coefficients are all real because we're told that k is a real number. And because of that, the conjugate, let's see, we're up to C3 now, the conjugate will be a solution to the problem. And C4, the conjugate of this one will be a solution. Conjugates, because polynomial is or has real coefficients. Okay. Now, if you had an equation like z cubed equals 8i, for example, this has got 3 solutions to it, but because there's an imaginary term in it, the solutions aren't conjugate pairs. Okay, the reason why they come in conjugate pairs is because we know that the sum of the roots is related to the coefficients. And if the coefficients are real, then the sum of the roots the imaginary stuff must cancel in it. And if I add up these 4 roots, I can get the value of k. The sum of the roots is equal to minus b over a for a polynomial. And make sure that you don't write down minus 2 minus k here, because actually we need to use the power of 5 term, the term that's actually not there. Okay, b is the coefficient, a is the coefficient of the first term, so a is equal to 1. And b is equal to 0. So the sum of the roots must be 0, and if we add up all of these roots, well, they actually just all cancel. What that means is that the last 2 roots are going to also be conjugates, and they could well be complex conjugates, or they could be real. But bearing in mind that this is a disguised cubic equation, disguised cubic equation with real coefficients will always have, a cubic equation, sorry, will always have real solutions. So the last two solutions I'm believing are going to be real for this. But let's try and work out how we get that. That's where we use, the sum of the roots didn't help us because we know they all add to 0, but the product of the roots is equal to, for an even polynomial, it's just the constant. I'm writing constant because what letter of the alphabet are we up to? Probably like F divided by A. For an odd power, it's negative, the last term. So for example, quadratic equation, the product of the roots is equal to minus C over A. For a cubic equation, the product of the roots is equal to D over A. Ah, gosh, stuffed that one up as an example. The even polynomial, even up to a squared, will be a positive number there, and the odd one will be a negative there. And so we're in an even polynomial going up to power of 6. So our product of the roots is equal to the minus of the constant. I just said minus again, I meant plus, it's even. So it's negative 25k because the constant is minus 25k. Right, so if we take all of these solutions so far and multiply them together, root 2 plus root 3i times its conjugate times the other one. Well, the other ones have got a minus and a minus, so I don't need to write them down. The minuses will multiply out to 1 times, I don't know what you want to call the other roots, alpha and beta. That's equal to negative 25k. What I'm trying to avoid here is solving, factoring the whole thing. If I can get around factoring, I'll show you how to factor in a sec, but I'm trying to just use the relationships between the coefficients to avoid heavy algebra here. Root 2 plus root 3i multiplied by its conjugate is going to be 2 plus 3, so 5. And we've got another 5 out of the third and fourth bracket. I squared's negative 1, remember, times alpha beta equals negative 25k. So alpha beta, my last two solutions, is equal to minus k. Alrighty, now what do we do? This is where I'm probably going to go to factorization. I need to know how to bring this 25 minus 2k in. For a cubic, that term's usually the paired products, but for a power of 6 equation, I'm not too sure. So, okay, let's factorize, even though I was trying to avoid it. Okay, I'm going to teach you something that's also quite sneaky here. If you have roots of root 2 plus or minus root 3i, they would have come from a quadratic equation. So if I rearrange this back to the quadratic equation, it's like a reverse complete square. I move the root 2 to the left, I square both sides. I've got x squared minus 2 root 2x plus 2 equals root 3i times root 3i is negative 3. X squared minus 2 root 2x plus 5 equals 0. Again, I could have used sum of roots and product of roots for that. The product of the roots there is 5. If I take root 2 plus root 3i and times it by its conjugate, I get 5. And the sum of the roots there add to 2 root 2, so minus 2 root 2 is the coefficient there. So the other one, C2 and C4, the conjugate pairs, are going to give a quadratic of plus 2 root 2 for that one, but a plus 5 will stay there. Okay, so we've got quadratic x squared plus 2 root 2x plus 5 times another quadratic, And then the third one, I was saying it had to be a real solution because we have a disguised cubic equation. Therefore, the plus and minus solutions are correct, which means that this here is going to be x squared, and we're going to have minus k there, are we? Does that contradict the earlier maths I had? The product of the two roots is minus k. Oh yes, no, that's cool, that works, because this one's got x is equal to root k and x equals negative root k, and when we multiply those together, we'll call that x1 and x2, or alpha beta, be even better, because that's what I had before. Alpha and beta, those multiply to make negative k. Alrighty, so there is the answer to the question. We could check that when we expand out this, we get back to the power of 6. The obvious things are like x squared times x squared times x squared gives x to the 6, and 5 times minus k gives minus 25k. But you need to check that you get x to the 4 having a coefficient of 2 minus k, and the 5, 3 and 1 terms all disappear. I'll leave that for you to convince yourself. But if you knew that the equation had to have a real solution, okay, cubics always have, I'm going to say not cubics, but real cubics always have a real solution. There had to be two real solutions, one the plus and one the negative. Alrighty, last question. The vertices of a regular octagon shown on the Argand diagram below represent the roots of a complex degree 8 polynomial. One of the roots is shown at the point A, 1 plus 0i. How kind of them to give us one solution. Okay. Now, the last time I did this question in class, I was pretty evil. I just gave my class the diagram and just said, go around and use geometry to find all the roots. Because if it's a octagon, you know that an octagon has got 6 triangles in it. So it's sides minus 2, 8 minus 2 is 6, 6 times 180 is the interior angles, divided by 8 and you get a 135 degree angle. So the octagon has an interior angle of 135 degrees, or if you think exterior angles, the exterior angles are all the same and there's 8 of them. So if you take 360 and you divide it by 8, you get 45 degrees. So it's quite a nice starting problem here. You go, oh cool, that one's 1, this one has to be I. And then you go, right, how much do I add to that to get to the next one? Well, we know that this hypotenuse here is root 2. So we need to add root 2. All the sides of the octagon are root 2. So this is going to be 1 plus root 2 times I. And then the next one's directly on top of 1, so it's got a real part of 1. We need to add another 1 to the 1. It's going to be 2 plus root 2. That's also got a real part of 1. 1 plus 2 plus root 2 I, and so on. But that's going to just be awful, because then you're going to have to go z minus 1 for the first factor, z minus I for the second factor, and so on, 8 brackets, and the question wants you to put it in this nice succinct form. So it's you're on a hiding to nothing trying it that way. So what you need to do instead is relate it back to your merit level understanding of the geometry of complex numbers. So I've run out of space because I got carried away on the last question. So let's just go back to this diagram. And Let's first up think about what z to the 8 equals. Let's just pick a nice number. Z to the 8 equals 256. If I had this, there would be a real solution of 2. There would be an imaginary solution of 2i. There would be a negative 2. There would be negative 2i. And there would also be the other 4 in between, and it would make an octagon. The roots would all be equally spaced. Now you would have learnt, if you've done de Moivre's theorem and some merit level questions, you would have learnt the first step is to turn this into polar form by writing 256 cis 0, and then you take the 8th root. The 8th root gives you the first solution. The 8th root of 256 is powering that by 1/8. You get 2 cis 0, or 2, and then the next solution is 2 cis pi over 4, because you add 45 degrees to get to the next one. If you've got to have them equally spaced, they have to be 45 degrees apart, and so on. And you just go around writing those solutions. Now, our problem is slightly different from that because it's centered at a different position. Okay, it's not centered at the origin, it's centered up there. And that is where the shift comes in. Okay, the shift in here is like when you shift a parabola or any other function. If you want to shift it to the right, you put a x minus usually in your parabola, right? So something like y equals x minus 3 all squared as a parabola shifted to the right by 3. We don't just want to shift it right, we also want to shift it up. But we don't have to put a number at the end to shift it up. We can just put a complex number in the inside. So the center there, this is the a plus bi. So that's quite neat. And the other thing that's a bit different is that if I was to shift the solutions to z to the 8 equals 256, if I was to shift them to the right and up, the solution, there would still be these two solutions here sitting on the horizontal axis of symmetry. And we don't have that. This question here, our solutions are above and below. If I had given you z to the 8 equals negative 256, when we turn that into polar form, we still get 256, it's modulus, but we'd get cis pi. When I take the 8th root of that, I'd get 256, no I wouldn't, I would get 2 cis pi over 8. Okay, and then my next angle would be pi over 4 bigger than that, so pi over 8 plus pi over 4 is 3 pi over 8, and then my next one would be 2 cis 5 pi over 8, etc. And that is what we've got here, because this first angle is pi over 8 above that horizontal axis of symmetry. The angles are spaced by pi over 4, so pi over 8 it is, and therefore our q, which is here, needs to be a positive number, because on the other side of the equation it would be a negative. Okay, so we need to find the center, and we need to find that q. Now, the q is going to relate to the radius of the points, how far away they are, because 256 here is 2 to the power of 8, and 2 was our real solution. And the only difference with the other one was that this was minus 2 to the power of 8, so our radius was still 2. All the solutions were still 2 away. Okay, so we've got two things to find now. We've got the radius and we've got the center. Now remember, we already knew this was 1 and we knew this was I. We knew that the length of the octagon was, rather, side length was root 2. So this is going to be 1 plus root 2 over 2 times I. And this is going to be 1 plus root 2 over 2. In the real direction, so our center, a plus bi, is equal to 1 plus root 2 over 2 plus 1 plus root 2 over 2 times I. And how do we find our radius? We need to use some trigonometry for that. Let's make a triangle there. It's an isosceles triangle. R there and R there. So we can split it down the middle. And what do we know about that? Well, we know I've just halved the interior angle. Remember I said it was 135 degrees before. So if I divide that by 2, I've got 67.5. Do I really want to do that? It's not a special angle. Yeah, I guess I'm going to have to, because this dude up here is 22.5. It's half of 45. No, I don't want to use right angle trig when it comes into half angles like that. So is there a different way of doing it? Of course there is. Let's go with the 45 degree angle and not split the triangle in half. Because remember, we have our trigonometry for non-right angle triangles as well. If you learnt it, it would have been in level 2 NCEA. This length was root 2. Let's call this theta. Oh, no we don't. Let's call it 45 degrees because it is. Use the cosine rule. Root 2 squared equals r squared plus r squared minus 2 times r cos 45. Root 2 squared is 2. We've got 2r squared times 1 minus cos 45, which is 1 over root 2. Divide both sides by 2. R squared is equal to 1 over 1 minus 1 over root 2 times top and bottom by root 2. And therefore r is the square root of that. We don't actually want r though. We want r to the power of 8, like I had before with 2 to the power of 8. And I've already got r squared there. So r to the power of 8 is going to be taking this and powering it by 4. I'm just going to get the calculator to do it because I can't be bothered doing the conjugate stuff. Root 2 minus 1, hopefully it just comes out as a nice number. My calculator's dying, the one that's updated is dying, so let's see if it will do surds for me. Didn't come out as a nice decimal when I did it before. Root 2 divided by root 2 minus 1 all to the power of, oh okay, well root 2 over root 2 minus 1, if you do the conjugate stuff, is equal to 2 plus root 2. Okay, it wasn't as ugly as I thought, to the power of 4. And then if you power that by 4, it comes out as 68 plus 48 root 2. My decimal value was 300 and something, which seems about right. Yeah, oh no, 135. This is my other calculator. What did the other calculator give? Yeah, 135-ish. Okay, so that there is almost the answer to the problem. Sorry for the mess here, but we just need to make it clear what q is equal to in that polynomial. And because when we find the roots for z, we want to, we'd put into apologies, we'll put a 0 into there, and then we'd want the q on the other side is, it would need to be a negative to not have any real solutions. And so our q must be a positive on the right hand side of the equation. So this is equal to q positive to ensure z minus stuff 8 equals negative. There is one other thing you could do in this problem, and we never used the z equals 1 root. If you wanted to, you'd have to know that the centre was equal to a plus bi, but if you wanted to, you could have subbed in z is equal to 1 to find that that Q value. So let's just get rid of all this stuff. And just show you one last way before this video. If it's not long enough, it's going to be a little bit longer. We could start off with z minus 1 plus root 2 over 2 plus 1 plus root 2 over 2i. Oh, my bracket's in the wrong place there. I've only just noticed it. It's got to be that in front of the I. Good thing I extended the video a little bit longer. Right, and then we want to power that by 8. And apparently that's going to equal negative Q if I sub in any of the roots, because that would make P of z equals 0. So subbing in one of the roots, like z equals 1, and just get the calculator to do the donkey work. So I know it's dodgy, but at least you can check your answer. So I'm subbing in z equals 1. That's going to cancel off with the just checking I've got enough brackets in there. It's going to cancel off with the first part of the real term, 1 plus root 2 over 2. I need to do what infinity plus 1 does and have an emulator for my calculator so you can see what I'm actually typing in. The suspense is just great in these videos, isn't it? And then power that by 8. And hopefully I've done it right. Oh, low batteries. It won't do it. It won't do it. So you just check that. It should come out to be equal to negative Q, which is the negative value of what we had before. As always, it's been a pleasure to teach you, and we'll look out for the next video next week. I'll be doing the 2010 paper. Bye for now.